See whether I have the right. This talk is by Dr. Sunil Kumar, Shear induced ordering in branched living polymer solutions.
Thank you. Okay, let me begin by thanking the organizers for giving me this chance to present this work. The work is about shear-induced ordering in branch living polymer solutions. It's actually models for living polymer solutions, I should say. So it's not experimental, it's a simulation work. And this work is done with graduate students Snigdha Thakur and Pratyusha Kea, and with other colleagues Abhijit Deshpande and Mohammad Nalaraji. Okay, so before I go into the model, some motivation for doing such work. So we all know that amphiphilic molecules like this, a cartoon shown here, like having a hydrophilic head group and hydrophobic tail, can aggregate into various forms in polar solvents. Right? You could have micelles, you could have spherical micelles, you could have cylindrical micelles, inverted micelles depending upon what solution it is, and columnar phase, lamellar phase, etc. So this cylindrical micelles, which is of interest here, is also called living polymers because these objects form by self-assembly and they can break and rejoin, and so they are always in a dynamic equilibrium in solution. Okay, so because of that, they are called living polymers because the length can change, length can fluctuate as a function of time. Okay, so this scission recombination under thermal fluctuations make these systems quite different from the conventional polymers that we know. So that's so the model which I am trying to present here, or I'll be presenting here, is motivated by this, even though matching it exactly to these systems is not possible at present. Okay, so why the system so interesting? Because as I said, this is again another picture of that micelle, and you can see that they can branch. Okay, they normally form these branches. Okay, again depends on salt concentration and solvent conditions, etc. They can form branches, multiple branches. And these branch systems can then form, make the solution into a gel. Okay, so there's a fluid to gel transition as a function of concentration of these micelles and also of salt. Okay. And these systems in the solution form, even before the gelation point, okay, exhibit very interesting properties. Okay, so for example, if you take a solution of CTAB in a big cylinder, and then this is an experiment which is done by Jairam and et al., and in which they have a big cylinder of CTAB solution in which they drop a polystyrene ball. Okay. And this is an experiment which we all do in early in college. So where we take an oil, a cylinder full of oil, and then you drop a ball, and then you look at the terminal velocity. So here they were doing the same experiment now with the CTAB solution, 9 millimolar equimolar solution, CTAB plus sodium salicylate. Okay, and then they drop this ball, and then they find that the velocity of the ball actually, instead of reaching a steady velocity, it actually oscillates. So they try to explain this by saying that there are when the ball moves through the system, there are shear-induced structures which are formed. Okay, and these structures change the viscosity of the surrounding medium, and hence it slows down the ball, and when the ball slows down, these structures disappear, and it starts moving fast, etc. But then subsequent experiments showed that at the shears, which is at the shear which is active at this velocities here, there is no shear-induced thickening of the system. So this phenomena still is not very clearly understood. Why does these oscillations happen? And anyway, these systems are also known to show shear-induced gelation. Okay, so here is a picture of here is a graph from Liu et al. In 1996, where they show there is a shear-induced as you increase the shear rate, you find the viscosity going up. Okay, this is the gelation point, and then there is a shear thinning at a higher viscosity. At very high viscosity is always shear thinning, which is fine. And they also exhibit what's called the shear banding, in which you have the system phase separating into dense and into two different densities. Okay, and with the micelles. With a micelle-oriented regime and an unoriented regime, so it's like a pneumatic-like regime and a fluid-like regime, which show giving rise to birefringence. And then there is this famous Rio chaos thing, and there was a lot of experiments which started off with this particular paper and been carried out by many people after that, like as Ganpati here has done a lot of work on that too. Okay, so that is the main reason why we thought maybe it's interesting to look at a model which can give us this fluid to gel transition in a living polymer solution, and look at what happens to this model or system when you shear it. Okay, so that's the main idea of the thing. Okay, so going back, there have been other models in the literature, and there have been many other models actually, and the most interesting to me at least was this coming from the group of Padding and Boyk. Okay, there have been a lot of work on this. So they actually start by them. They actually start off with looking at an atomistic simulation of EHAC, okay, and urate and okay, there's a mistake here. Urate and EHAC surfactants, okay, and then so they obtain actually in the atomistic simulation they're able to get the long micelle forming, okay, and this they use this simulations to get an idea about persistence length, elastic modulus, scission energy of these micelles, okay, in the atomistic level. But of course they can't simulate anything more than one micelle in this atomistic level models. Okay, so they went to MD simulations of coarse grain models, basically taking this starting from this, coarse graining this now, okay, and trying to match the parameters of the coarse grained model interactions such that they have the same elastic modulus, scission energy, etc. And then from that, but that also cannot really take you into any rheology kind of simulations because it's still too detailed. Okay, so then they went to, from there they go into doing a Brownian dynamic simulation. Now it's simply Brownian dynamic simulation. No. And then by looking at rods, okay, so each of this rod is of the length, is of the persistence length of this micelle. Okay, so now then they have the scission energy, the scission of these rods put together, the scission of these bonds are again, scission energy is again matched or obtained from this coarse grained models. Okay, so that's kind of a hierarchical model they build up. It's but at the end ending up in a Brownian dynamic simulation. So we wanted to use a model which will have the hydrodynamics built in. Okay, so we used a slightly different approach, which we are using the dissipative particle dynamics model. Okay, for simulating these fluids.
This model, they had the missile is in a fluid. This thing.
Sorry.
It's in a fluid.
This one?
Yes.
Yes, of course, in water. Yeah.
Okay, but how do they take the hydrodynamic interaction into account then?
See, this is an MD simulation here.
Okay.
Okay, in an MD simulation, there is no hydrodynamic interactions. It's all done using a thermostat which wouldn't conserve.
But if it's a missile, then hydrodynamic interaction is supposed to be important, right?
For formation, it's not important. It's only if you want to look at the dynamics of the micelle, then it is important. Okay, but the hope here is that we just want to look at. They just wanted to look at here, do this simulation just to get the elastic modulus and the persistence length. Okay, and of course they also get the scission energy. The scission energy might depend on the dynamics. I agree. So, but this model has no aerodynamics in that. Okay, so that's the point. We wanted to have a model which we can take aerodynamics into account, and that's the reason why we went to doing a dissipative particle dynamics model. Right. So, just a quick introduction to dissipative particle dynamics for those of you who doesn't know it. Okay, so it is something like a molecular dynamics, but always for coarse grained beads. Okay, so there is no molecule in this; there is only dynamics. Okay. And most of the time the interactions between particles are soft repulsive, okay, and you have many particles and they all interact repulsively, and depending upon the strength of these repulsive interactions, you could have attractive interaction between certain particles. And so it's a mesoscopic model, okay, and the most important thing about this model is that it's the thermostat, okay. The thermostat is for this model is constructed such that you have dissipative pairwise forces and random or stochastic pairwise forces, okay, and these pairwise forces assure that you have the local momentum conservation, and hence all aerodynamic interactions are preserved. Okay, so you can for those of you who are not interested in the detail, it can be you can think about this as an MD with a very special thermostat. Okay. So as I said that you have the dissipative random forces, and on top of that you also have the conservative forces. Okay, that's pairwise repulsive forces. So that's what I'm trying to show it here. So we have n DPD particles. Okay, let's remember that this is a coarse-grained kind of model. Okay, so there are n DPD particles, so they are not really atoms or molecules. Okay, interacting with dissipative random pairwise interactions, conservative, dissipative, and random pairwise interactions. So this is a conservative force, and so this is the strength of the interaction, the force. Okay, and this is a function which is which tells you the nature of the force. So you take soft repulsive interaction with a cutoff RC, so it's 1 minus R by RC. Okay, that's a force acting, and for R less than RC, 0 for R greater than RC. So it's a soft repulsive interaction between particles. Okay, and then you have the dissipative force, which is modeled as Rij dot Vij. So that is Vij is the relative velocity of two particles. So the component of the velocity, the difference in velocity which is along the line connecting the two particles actually contribute to the dissipative interaction. And that form is taken in this in the DPD model to assure that there is Galilean invariance in the system. Okay, then there is the random force. Okay, the random force has the dissipative force has a strength gamma, and the random force has a strength sigma, and the weight functions for the dissipative and random forces are taken to be the same, is that R equal to 1 and D equal to 2, and or in this fact they are related by this function. Okay, but we take the omega to be always same as 1 by R minus RC. So omega is the same in all of these cases. Okay, and theta is a random number with 0 mean and unit variance. So that's the system, okay, which we have. And of course, sigma and gamma and sigma are related through this relation, and that kVt fixes the temperature. Okay. So fix the temperature and then choose one of them, and then you can choose the other one, but through this relation, and so that you have the thermostat. That's the system. Okay, so so because of soft interactions, we can actually go for large time integration without the system blowing up. Okay, and that's only the reason why one keep the soft interactions. It is not necessary to keep the soft interactions. One can also model other interactions using this thing. As I said, DPD is basically this thermostat. Okay, not really. That's not really important. Okay, you can choose that. Other interactions like Lennard-Jones interactions too. Okay, so what is our model for this fluid for this micellar system? And this is our model. So you take a micelle, okay, and then you have the head. So you have these three parts. Okay, we just model into a trimer. Towards the end of my talk, I will show you also for tetramer and pentamer models. So we take our basic unit as a trimer. Okay, and then so there are two end beads. Okay, which are marked A here, and then there is a middle bead which is marked I. And then apart from that, you have the solvent particle which is marked W here. Okay, so now the interaction between these head beads, okay, the two head beads, right, so is given by this kind of a potential. Okay. So there is a barrier to cross. Once there is an attractive well, okay, so and then there is a once the two particles go closer than the barrier, okay, then it gets into this attractive well, and hence it can form long polymers. So the idea is that there is an n cap energy. Okay, so when these two segments come closer, and okay, once it overcomes that n cap energy, and they can form this mice, okay? And then they can form this network like that. Okay, the middle bead interacts and the water and water particles and water and this middle bead interaction is the same. So basically, the water actually wets the surface. That's the idea. Okay. So that's the basic model. So remember this potential, that is, and then what we varied in the simulation is actually basically the depth and the depth of this well and the height of this barrier, and then we look at different regimes. And apart from that, we also have the model. Actually, it's a semi-flexible model. Okay, so you also need there's a persistence length. There's a non-zero persistence length for this segments. Okay, so that's modeled by three-body interactions. So there are two types of three-body interactions. So one is between these particles to keep them stiff like that. Okay, so that will be given by a 1 minus Rij dot Rik kind of interaction. And when there is another interaction between these two particles. Okay. So whenever these two particles come closer than this distance R3, okay, then they are considered bonded, okay, and then you have a three-body interaction acting between them. So you have a long straight micelles forming. Okay. That's the idea. Okay. So remember that. So since everything has to go smoothly to zero, all the forces. Okay, so that's why we have this function here. Okay, so that makes sure that once the particle goes above R3, the forces are going to zero smoothly. So to conclude the interactions here, so for the N beads you have an interaction like that, or for the micelle beads, okay, so this the streamers, so you have an interaction like this. You have a conservative force acting the normal DPD conservative force, and the dissipative and the random, okay, and then you have this N bead interaction, and then you have a three-body interaction. It's N bead interaction like this, and then there is another three-body interaction. So that's the whole. Okay. So we take a simulation box of size 40 and put periodic boundary conditions. Okay, choose density 3. This is a standard density which is chosen for water in DPD interactions because that gives you the correct compressibility for water. Okay, and you have about 1,92,000 particle. Okay, and then you have a resting length for the AI. This springs to be 1. Okay, and this to be 2. So that this is actually a variable too. We can change that range of the interaction too. Okay, so that's detail about the simulation parameters. Okay, so that's a system which we are going to which we simulate. Okay, so at this stage, is there any questions? Is the model clear? Right. So the most important parameters, of course, as I said, this kind of barrier crossing. Another one is that you have this three-body interactions to keep them stiff. Okay.
Is there any merit in keeping the water molecules explicitly? Could you just model hydrodynamic interactions in the interactions between beads?
Then you have to have a mobility matrix, and like the Brownian dynamics case, right? You can do like that, but there is I don't know there is any specific advantage in doing that way. This is easier, I think, to do.
Why? Because
for the systems.
You could take bigger systems or something?
Not really. No. The mobility matrix is also difficult to calculate for bigger systems. Yeah. Okay, so I can talk to you about it because I've also done that simulation, so I can talk to you about it. Okay, so and also in this case, there's one more thing which is in this case is that the difference between doing that is that here what we have is just this potential, okay, and for the N bead interaction, okay, and a repulsion between the N bead A and the water. Okay, basically the water doesn't like the N beads don't like the water, and then they like to come together. Okay, so it's kind of self-assembles here. Okay, and in the case if you don't have an explicit water, then you have to have some other attractive interaction between these two beads. Okay, that's all the difference is, apart from calculating the mobility tensor. Okay. Okay, so now we go to the results. Okay, so now here I'm showing the number of branch points as a function of concentration. The concentration here C is actually the number of the ratio, the relative concentration between this micellar beads, okay, versus that of water. Right? So it's 3%. This is in a percentage. So this is at about 3%. You start seeing the branches for this micelles forming. Okay, so you can see a branching, right? And you can look at the diffusion coefficient of these beads, okay, as a function of inverse concentration, and you can see about 3.5 is where of this concentration 3.5 is where you start seeing where you see the diffusion coefficient goes to 0, and that's kind of gel point. Okay, so when the concentration is about 3.5, okay, the system forms a gel. So that is just the detail of how we compute. Okay. So at low C we have a fluid phase, and at a high C we have a gel phase. That's what we see here. And so if you look at the organization of these polymers inside at these concentrations, okay, you see that at C equal to 2 it's like a fluid, and C equal to 3 is also a fluid. Okay, but you can see that already larger things have started forming. Okay, and on increasing C you see gel phases. Okay, now this is what I'm showing here is actually a cross section of the whole simulation box, just taking a small slice so that you can actually see the structure. So you see the completely cross-linked branched structure, okay, forming this gel phase here. And so as you said that this happens at around 3.5. Actual gelation point is at 3.5. Okay, this is a problem. Okay, so now here we look at the segment length distribution, which is an exponential distribution. Okay, and so the segment length, as I increase the concentration, okay, as I increase the concentration, the segment length first increases. Okay, that means it's forming this big micelles. Okay, and once it starts forming these branches, the segment length is actually from one branch point to another branch point, or so that segment once it starts forming these branches, the segment length distribution becomes it comes down. The maximum length it has comes down. Okay, that's what this point shows. We can also look at the cluster size distribution, okay, of this system. Okay, and you can see that at 3.5, okay, you have a power law for the cluster size distribution, showing that this is just random percolation, which is doing the gel is actually formed through random percolation of the. So the exponent is 2.5, okay, which is the random percolation exponent. Okay, so that's what you get find here. Okay, so now again, so we have an exponential distribution for C less than this particular value C to 3.5, and a power law for C equal to Cp. Okay, and so the gel phase actually contains spanning clusters, and so we can see that as you go above this, you start getting another peak there. Okay, which is showing that there's this big spanning cluster which happens. Yeah.
So when you see branching, is a physical branching in which you have the local Micellar curvature going from positive to negative, or?
So we don't have that here, right? We just only have this. Yeah. So we just have these beads. Okay. So basically saying that there is an attraction between this n beads. Okay. So if you don't have this three-body interaction, okay, then you will actually get a spherical cluster of all of them coming together. So it's a three-body interaction which controls the branching here, okay, because they want to be straight. Okay. So the only parameter here which controls the branching is three-body interaction. Okay. And in real system, it will be salt concentration and things like that. Yeah. So, okay. So that's the cluster size, the distribution, and sorry.
What do you do with a gel?
Well, we just look at the diffusion coefficient.
But it could be caged and then.
No, we look at the long time diffusion coefficient. Yeah. Yeah. I'll come to the diffusion coefficient again in a minute. I'll come back to that because there is also. I'll come to that when I talk about it. Sorry? We do. You'll see that. Zero shear modulus, it's the same thing. Yeah. Zero shear modulus. Yeah. I'll show you that the shear modulus. Okay, so then we compute just to get the relaxation times, we compute the self-intermediate scattering function. Okay, and that's what's shown here for different Q values. Okay, and then the integral of that, which gives you the relaxation time. Okay, so we look at that as a function of Q, and we find that for large Q you have a Q cube, and for small q you have a Q square. Okay, showing that there is hydrodynamic interactions at large length scales, small length scales. Okay, and the crossover length scale here is actually almost a trimer size. Sorry.
That's a relaxation time.
Yeah. Yeah. It's aerodynamic interactions. Okay, then you have a Q squared, one which is at a larger length scale. So it's diffusive. Okay, so it's the same dynamics at large Q and diffusive at low Q. Okay, so that's what we find in this model, relaxation time.
The Q
On those length scales, you don't expect Q squared even if your dynamics is diffusive, no? Because you have the structure factor that plays a role.
At large length scale, you'll always get Q square, right? No? This is below the. This red one is for below the percolation transition, okay, and the green one here, what you see is the one which is above. Okay, there you have a smaller Q square region.
Sunil, the question is,
Yeah.
where is Q times RG in that plot?
Yeah.
Is it at 1?
It's about 1, yes. Yeah. That's where you see the. Okay, so is it okay? Correct. Yeah. Okay, so now we also look at the recombination time, the fission and recombination time, which we can measure here. Okay, so basically the recombination time is the time at which, so you start the clock at when some bond there's a scission. Okay, and then you ask the question, when does it recombine again, with itself or with something else? Okay, so that's the time which we count. Okay, so that's a distribution of the recombination time. Okay, and that follows exponential. Okay, and there have been paper by Beno, I can't read that name. Okay, and so which shows which explains why this would be exponential in that regime. And so you can also get, so this is at low concentrations where you have exponential recombination time. Okay, and at high concentrations you have a power law. Okay, now the difference between these two is that here that it's mean field like. Okay, so you have a scission happening. Okay, and then it has equal probability to combine with any other micelle. Okay, while here you have a scission happening, it has a higher probability to combine with itself again. Okay, so that's what leads to the power law in this case. Okay. So actually you can see that this is again a slice and at very short time run. Okay, just to show that things break and then join again. So that is you can see that they break and join at these points. So this is what I was trying to explain. So you can have this two yellow curves if you can see it. Okay, so they can break. Okay, and then they can join with itself or they can join with some other micelle. Okay, that's the two difference. So you can have at high densities as you go to higher concentration. So you have it always, most of the time it's actually joining with itself. Okay, so that's what leads to this power law behavior. Okay, so this is called diffusion control regime and that's called mean field regime. Okay, so then we compute the stress and look at how the stress relaxation happens. Okay, so that's what has been shown here. Okay, so stress relaxation follows the 1 over root t exponential minus t by tau. So again, this 1 over root t here comes from the fact that there is this scission and recombination. Okay, so that has been worked out. In this paper here. Okay, so we see the same. We see that we can fit our curves into that into this function. Okay, of course we have these oscillations here, which comes from this bond, the spring oscillations. Okay, so that's the reason for this. We find this oscillation, and we also have a residual stress once that's a finite size effect. Once you have a cluster, once you have the spanning cluster, okay, and then you have a residual stress coming from the fact that these bonds are a bit stretched to make the ends meet. So that is at larger concentrations above the threshold. Okay, so we can so we see that we can compute we can look at in this model, we can look at the scission and recombination time scales and the distributions, and we can look at the stress relaxation, and we find that all of them obeys the expected behavior for living polymer things, which has been predicted by theoretical calculations. Okay, so we can be fairly confident about this model that it kind of gives you the expected equilibrium answers. Okay, so then we start looking at the shear effect. Okay. So the way we do the shear in two different ways. Okay, one is having a simulation box having hard walls at the two boundaries. Okay, and then moving these hard walls at fixed velocities. So and then another way of doing that is to have the Least-Edward boundary condition. Okay, but so we do Least-Edward boundary condition only to check our hard wall results. The reason being that the Least-Edward boundary conditions, once you put the Least-Edward boundary condition, we are not able to parallelize the system, so we can't do very big systems. So to go to very big systems, we would do the hard wall boundary condition. So that's and we find that there is no difference between these two vessels. Okay. So we have for the time being, you think about that, this wall is moving that way, that wall is moving that way, and then the micelle solution is inside this, and the micelles actually wet these walls. So okay, and then that's what the simulation is shown here. Okay, so we shear the system at the gel phase. Okay, and we find that once you shear them, okay, they may start forming these layers. So they layer, okay, at a particular shear rate. Okay, so low shear rate there is no layering. As you go to higher shear rate, they form this layered system, and the spacing between these layers is actually given by the range of this interaction. Remember that potential which I had shown you. The range of the interaction actually determines the spacing between these layers. I should admit that I don't really understand how these layers form. Okay, but you can see how does it vary as a function of different parameters, which is what we have done here. So sorry.
You have a hard wall.
Yeah.
If you have a hard wall, even if you don't have a shear,
I know.
also.
You don't get layers. We checked that. Yeah, we checked that. Yeah. So what Sarjit was asking is that when you have a hard wall, okay, so of course there is already a density modulation there, but that doesn't lead to layers. Yeah. And that's the reason why we did this Least-Edward boundary condition also, to just check that it's not coming from the wall-induced thing. And also there is a critical shear rate beyond which you don't see, below which you don't see this layering. Okay, so. Sorry?
It's not a matter of time scale.
No. We run it long enough to see it. Yeah. We can see that the velocity, we can look at the velocity profile, and then that equal. And also you can look at the stress in the system, and that will also equilibrate. You can see that the stresses are the same. Okay, so now here is what I have shown here. So this is again, so that you get this layered structure, okay, at shear rate. Okay, and so these are various parameters used, gamma dot equal to 1. Okay, and if you look at each of these layers, okay, you see that it is still more or less connected cluster. Okay, so so within the layer, you put these parameters, and for this within this model of DPD model, okay, you don't see any particular orientation. Okay, but things all in this direction there is a strong layering. Yeah, the sliding path, so the viscosity drops and things like that. So they slide past each other. Okay. So then, what we did was, as I said, that we found that this layers, the layer spacing, it depends on the range of this interaction. I said, okay. So then we thought, okay, and then each layer is already quite crowded. So we were interested in seeing what happens if I increase the range further. Okay, so that now each of the layers has to get more and more crowded. Okay, then what we found that is then once you do that, okay, then within the layer itself there is an organization, and you get this columnar phase in that layer. Okay, so at a higher range of interaction, which of the end beads, okay, then you get a columnar phase. Okay, so this is showing that each of this. What I'm showing you is each of this layer is shown here as columns. So that depends on where they are, right? So this is 20 here in these units.
Is there a rolling motion?
No, I have not seen rolling motion. No. There is periodic boundary in that direction, of course. Okay, in this case, the periodic boundary in that direction, so it goes and comes back. Okay, periodic boundary in both directions, this and that, in this perpendicular direction. Okay, so that's what we see here. So we see the columnar phase as you increase the system size. Okay, now this is the viscosity. I don't know. You can see the green line. So this is related to your question about what happens. So the viscosity, if I look at, okay, this is for 5%. Okay, and you can see the viscosity diverges for 0 shear rate. Okay, and for this system, it's showing that that's actually a gel phase. Okay, and for below that concentration, you see the viscosity there's a plateau, and then it shear melts. Basically, it has a shear thinning. Okay, at this set some value of shear rate at which this layer starts forming. So the alignment of these polymers leads to decrease in viscosity because they can now slide past each other. Okay, so So then we look at, so we want to know whether there's anything special about this trimer, okay, or if I go to tetramer or pentamer, what do I see? Okay, so that's what we are looking at here. Okay, so this is the case with tetramer, and so this is the case of a tetramer. Okay, so then again, so you can see that there is a power law. This is again cluster size distribution. Okay, and you can see this blue line, which is a power law. Okay, which happens at 3% now. Okay, which happened at 3.5% in the case of trimers. Okay, and in this case, when you go to tetramers, okay, you have it happening at 3%. Okay, so larger segments means the percolation happens at a higher, at a lower concentration. And so for a pentamer, okay, it happens at 2.75. Okay, now this is 2.75 and 2.6. So it's what happens around 2.75. So as you go to higher segment length, you have the percolation, which happens at a lower concentration, as we know in polymers. That's how it goes. Okay, for the gel formation in polymers, it's known that for the larger the molecular weight, the lower the concentration required for gel formation. So that's what we see here also. Okay. And so for the larger segments, the percolation is at a lower concentration. The interesting thing is, if I look at the diffusion coefficient, okay, and so if this is again 1 over C, okay, diffusion coefficient for tetramer and trimer, tetramer, and pentamer as a building block. Right. So for large concentrations, of course, the trimer diffuses the fast, okay, and then the tetramer and then the pentamer, okay, it goes there. Okay, but low concentrations, at low concentrations, there's a crossover here, okay, and you see that now the pentamer is the one which is this is actually beyond when it goes beyond the gel forming thing. So you still have a non-zero diffusion coefficient, which is small. Okay, it's about order of 10 power minus 5, but you can see that there is a reversal in the behavior. And this we try to tag the end bead and then try to follow that. Okay, and then what we see is that this actually comes from the fact that once something breaks, okay, one of the junctions break, and then this has to bind with something else. So it can actually go from by joining to one bead to another bead by tumbling like that. Okay, so that is of course dependent on how big the polymer is. So the larger the polymer is, the segment is, the larger it can, the faster it can move. So that's what's happening in this regime. While here it's a normal diffusion. Okay, so I think so then there is then we look at the effect of the strength of the interaction, okay, at the end bead interaction, okay, and that's what's shown here. Okay, it's all for trimer. Okay, so different strength of the interaction, 0.1, 0.51. So if the interaction, the end bead interaction, that means the depth of that well, which I showed you in the beginning, if it's low, okay, then you don't get any layering when it shears. This is all for gamma dot equal to 1, all of them. Okay, so you don't see any layering. As you increase the interaction, you have so 0.5, you have a coexistence actually. You have the layers formed here, and there is no layering seen here. And as you increase the strength of the interaction further, then you get a complete layering in the system. But the layer spacing here and here are the same. So layer spacing definitely doesn't depend on the strength of the interaction. Okay, but the gamma dot required to get the particular get this transition from the gel to this layered state depends on the strength of the interaction. So that's the dependence on the end bead. So it's actually this polymer, once it starts, one of the polymers starts moving, it actually literally pulls the other polymer towards it, and then how effective it is in pulling that polymer decides this. So that's been decided by this strength. So for the same shear rate, okay, and for the same interaction strength, that is 1 for that, okay, and you need a higher shear rate to get layering in tetramer and pentamer. Okay. So as you go from trimer to tetramer, you need a higher shear rate, okay, to get the layer things. Okay. So there was problems in the numerical problems in simulating a higher shear rate in this model. Okay. So what we thought was, okay, if you could change the viscosity of the embedding fluid, As in, we could probably see whether there is an effect of, we would get this transition at a lower shear rate. So of course there is one problem with this DPD model. The DPD model, the Schmidt number, okay, which is the ratio of the particle diffusivity to the stress diffusion, okay, is 1. So that's very low. Okay, in real fluids it's about 1000. Okay, so that means if I start, which means that if I take water, this DPD water, and then I start shearing, it takes a long time for it to actually set up a linear linear velocity profile. So we went to a slightly different thermostat from here. Okay, that's what we are doing now. So that's just a new result. So we went to this using this Lowe-Anderson thermostat. Okay, which is just a different way of implementing the thermostat. So now you take pairwise, instead of doing a pairwise conservative and dissipative forces, you have a conservative force as before. Okay, and then instead of having the dissipative and random forces, you take now two particles pairwise. You take one pair within a range. Okay, and look at what its relative velocity is, and then you pick up a relative velocity from the Maxwell distribution, and then you put that in here. Okay, and that's the way this is done. Okay, and it is shown that this kind of, and this is our results too. So we can actually simulate this. Okay, so we were able to implement this in our parallel code. That's what's shown here. So anyway, so this is a rate at which we replace this relative velocity from this distribution, okay, as a function of the Schmidt number. As a Schmidt number as a function of this rate at which we replace this, we execute this thermostat step, and we can see that as you increase this, you can get pretty high Schmidt numbers. So we went to a larger Schmidt number solution, and then this is looking for a tetramer. Okay, and then you can see that this tetramer, and you go to this, still it has to run for a long time, and say at a steady state when it goes, it forms its layers. Okay. So for gamma dot 1, as I showed you earlier, gamma dot 1, you didn't have a full layering. Okay, when you had the Schmidt number of 1. Okay, but when we went to a Schmidt number of 7, already you can see that there is layering happening. Okay. So it looks like viscous drag of the higher viscous stresses, of course, help setting up this layered structures much earlier. Okay. Okay, so that's about all I have. Okay, so to conclude, okay, so we have this model for the main things that we have this model which we have come up with for simulating this kind of living polymers. And as I said, in our case, the branching and the scission energy are all still parameters. We don't have a mapping to a real system. And the branching here is controlled by simply this 3-body interaction, okay, which tends to keep it straight. Okay, and then that way we can control the branching. And then we show that we have a fluid to gel transition, and then there is a thinning of the fluid as you shear it, and that thinning happens through this layer formation. And we can go to higher the segment length. You can, instead of looking at the trimer, you can also look at tetramers or pentamers, and you can still get this layered from the gel to layered system transition, the isotropic to layered transition. And as the molecular weight is increased, we see that the gelation happens earlier, but the diffusion coefficient, okay, seems to go up as for a pentamer than for a trimer for high values of the concentration. And so when you go to the building blocks are higher, means you need a larger viscous coupling to make this layers. Okay, and that's the conclusion. Thank you.
Sunil, could you please elaborate a little more about the diffusion coefficient for the trimer being different from tetramer and pentamer together? I could not distinguish between tetramer and pentamer.
Huh.
Right.
Yes.
So what is going on there? And also I want you to tell us about the C that you used to normalize your time. In that plot, if you could go back to that plot.
Time? No.
Yeah. D, trimer.
See,
the abscissa there, not here. The comparison between trimer, tetramer, and pentamer.
That's coming here.
There, right. What's your abscissa there? what is that weight percent? 1 over C? Is it 1
Oh,
over
1 over
C?
C. It's just a concentration.
Concentration. So how do you define concentration here?
So it's a ratio of the number of micelle beads to number of water beads. So you have this beads on this.
So how does the branching enter there? It doesn't enter in the
Branching,
concentration, just number of beads.
Yeah.
That's all right. So tell us, why is the trimer different from the other two?
Well, you expect this to be that you agree. Right? You expect this to be larger than this. Okay?
Right.
But why this jump from here to here and that?
I'm concerned between the green and the blue. Why are they so together?
Yeah, they are close. I thought I must be more worried about this one. Okay, I don't have much an idea why this is not linear. To tell you
Yeah,
the
right.
truth.
That's
So that
yeah.
I don't know.
Is it because 1 over C? No, I don't say
No,
that. You
it's
fix
nothing to
the
do with
C
1
and
over
say
C.
1 over
No.
C to 0.9.
No,
So
no.
why
First,
is that?
this is just a fixed concentration. For a fixed concentration of the number of beads, okay, I look at the pentamer and trimer.
So why
So
is that?
I don't have an idea yet.
I'm not sure my question's relevant, but I just wanted to ask, in your simulation, if you restrict the number of polymers that you're feeding into the system, do you alter Z at the expense of XY?
No, sorry, I didn't get
In
that.
other words, are you creating layering? So I'm presuming that in your simulations you're constantly providing.
No,
No.
no, that's fixed. The number of particles are fixed.
Right. So you're seeing. So.
It's just reorganization of the polymer things from an isotropic thing into layers. That's what you're seeing here.
Right. So your XY is actually changing. So
No,
okay, I'll
yeah, maybe I don't understand. Yeah, that's something.
Effect of temperature on this system, on the gelling concentration.
No, we have not changed temperature. We have run only for one temperature so far. Everything is scaled in terms of KBT, and that's kept one. So far, as you can say, is changing temperature because it's scaled by KBT. Okay. So,
To change?
yes.
This transition between the lamellar to the columnar phase, can you get it by a linear analysis of the steady states? So you write down coarse-grained equations for the, you're trying that, okay.
Not yet.
I would like to know about this, how this crossover point is related with the figures that you have shown in the next slide.
This one?
Yeah.
Yeah. No, so this is a no shear. This is a equilibrium, no shear. Yeah. This is measured at equilibrium.
Yeah, it's okay, but
Okay. Yeah.
you,
So what
you can
you,
see the diffusion coefficients, how they will be changing when the.
this point you're saying? I don't know whether it's even a point. Right? I won't vouch by that it's a point there. Means I wouldn't say that all these lines are actually going through one point there. Okay, I don't have confidence on that to say. What I can tell you is that this goes up. I do understand. Okay, that's because of this thing. As I said, you have all this branched. You think about a network. Okay, and from one junction it detaches. Okay, and then it goes into another point. Right, and the segment here, which does that. Okay, the segment length goes up from here to here. So then whenever it detaches from one point and attaches another point, it is traversing a larger distance for a pentamer than so that I understand.
So if there are no further questions, let's thank the speaker once again.